Now let's look at another property, which is complex ion formation. So these are the objectives we are going to follow so that we cover everything in order. So the first one is to define a complex ion. So by definition, a complex ion, I'll give you an example here so that we get to know or understand what I mean. So if we have something like this, or I'll take maybe something like dichromate. So these are what we call complex ions, and from what you can see that here we have more than one atom, making it a molecule bonded to this copper. Then this side we have oxygen atoms bonded to chromium. So by definition, we can define a complex ion as a substance in which a metal atom or ion is bonded to one or more ions or molecules through what we call coordinate bonds. So that's according to me, but however, you can find in some textbooks they can define a complex ion replacing these terms. So I've said that it can be a metal atom or ion bonded to one more or more ions or molecules through coordinate bonds. So instead of saying ions, they can say atoms that are negatively charged. Why are they emphasizing negatively charged? Because if you are looking at complex ions and the transition elements, remember all these elements, that transition elements will have positive charges, you get? So they will have positive charges, which means they can only actually they will only bind or form bonds with negatively charged atoms, you get? I mean ions, negatively charged ions. For example, oxygen can have maybe nitrogen, just like that. So that's why someone can say that its complex ion is a substance in which a metal atom or ion is bonded to an atom or group of atoms that are negatively charged, you get, instead of just saying ions. Then molecules, instead of saying molecules, can say an atom or group of atoms that have a lone pair of electrons, because you shall see that the basis of complex ion formation is that the transition elements actually have vacant d orbitals which can accommodate lone pair of electrons. So all these molecules that are bonded to it must be having some lone pairs that they will donate. So by definition, that's a complex ion. Then we can look at another one, which is ligands. So what are ligands? Ligands are actually these atoms or molecules that will be bonded to the central atom, which central atom in this case will be the transition element. Then the type of bond that's formed is actually a coordinate bond, or can also be called a dative bond, covalent, dative, something like that, instead of just coordinate. Can also call it dative. So in this type of a bond, you find that it's only one atom donating the electrons. You get, for example, I can have nitrogen donating its lone pair to, let's say, I'm just using an example, to, let's say, iron. So we normally use arrows like that one to show that it's the electrons actually coming from nitrogen to iron. So we can use straight arrows to demonstrate that. Then we can move on to the next. We have here what we call coordination number. I have abbreviated it as CN. But before this, we can look at what enables these transition elements actually form the complex ion. So you'll find that for any transition element form complex ions, it must have vacant d orbitals, that is unoccupied. Remember what we've just seen under formation of colored compounds? We had something of that sort, and we had, remember this? So whenever we have these vacant d orbitals, they can accept lone pair of electrons from other atoms, so that they form a complex. So for any transition element to form complexes, it must have the vacant d orbitals. Vacant d orbitals. That will accommodate the lone pair of electrons donated by the atoms or the ligands. Get the point? So that's the main point. But then you can also add on other points like having a small atomic radius. So when you have a small atomic radius, meaning you can easily attract what comes towards you. So this one also matters. A small atomic radius, that also contributes. So these are like the main points, but they are not the only ones. They can also be others, but always remember these two. So moving back to the key terms we need to define, we have here Cn, which is coordination number. So can have some more space here. So coordination number, what will be this coordination number? Coordination number is actually the number of coordinate bonds that can be formed between the central atom and the ligands. Take an example of ammonia. So normally ammonium ions, let's say hydroxide, or we can have this nitride, we can have oxygen, you get? So ammonium ions, this is the ammonia, but I'm talking about ammonium ions. So ammonium ions normally form one bond, you get? So normally form one bond, and that will be the coordination number. So that's one. The same applies to hydroxide and the cyanonitride. When you look at the oxygen, it normally forms two bonds with a central atom. Take an example of carbon with carbon, where we have such, you have two bonds. So this number of bonds formed is what we call the coordination number. And we are going to look at the different types of ligands. So from this I can build on and say that coordination number is actually different from ligands, number of ligands, because this is something we normally confuse. An example, if we have these diamine copper 2 ions, something like this. something of that nature. So if in this case I have two ammonia molecules, these will be the number of ligands, which will be 2. But the coordination number, you will count the number of bonds that will be formed between copper and ammonia, as we are going to see. So we have types of ligands. We have monodentates, we have bidentates, we have polydentates. So what are these monodentates? The monodentates are actually the ones that form only one coordinate bond. An example is the ammonium we have given, hydroxide, cyanonitride, and you can find more examples. Then if we talk about the bidentates, the common example here used is the ethylene diamine. Ethylene diamine. How do we write that? So you have your two amine groups attached to the ethylene residue. So you have the ethylene here, and then you have your amino groups like that. So this is the ethylene diamine. Why is it bidentate? It's because it will form two coordinate bonds with the central atom. But how do these two bonds actually come about? You see that we have two nitrogen atoms, both of which have lone pairs of electrons. So whenever they are in a bond, you find that this will donate and that will also donate, forming two bonds. I'll write here to illustrate. So if I have my copper, normally it binds with two of these. I can have my ethylene here, ethylene, and then attached to both ends are the amino groups. Have amino, even this side you have your amino group. So what will happen is that this nitrogen is donating its electrons. How do we do that? Remember, we use arrows. Even this side, you see that nitrogen is donating electrons to that. So you will also have another molecule, because copper normally binds with, forms a complex with two of these molecules. So you have something of that nature. You get? You have something of that nature. So in this case, this can be a very good example to explain the difference between the coordination number and the number of ligands. So if I look at this, how many ligands do I have? I have this one and that, which I have not written here, but there will be two ligands. You get? So there will be two ligands. Then when we look at the coordination number, which we defined as the total number of bonds formed, you will count these arrows, and that will give you 4 as your coordination number. So that's the main difference between coordination number and number of ligands. Then polydentates, finally, it's these are types of ligands which form more than two bonds with a central atom. A perfect example is EDT. EDT is actually defined as, or in full, it's what we call the ethylene diamine tetraacetate or acetic acid. So if you may need the name, I can write it here. ethylene diamine tetraacetate ions. So this is the common example we use, EDT, tetraacetate ions. Instead of acetate, someone can just say acetic acid ions, you get? So how does this look like? I'll draw it here just for your reference. Can move this slightly. So we shall have something in this form, ethylene diamine tetraacetate. So I have my ethylene here in the center. Then I have two amino or nitrogen atoms. But since we have these four tetraacetates, meaning each will carry two instead of the hydrogens. You get? So you have your acetate, which is normally written in that form, acetate like that. You get? Even that side you have your acetate ions, just like that. So this one normally forms a total of about 6 coordinate bonds, meaning its coordination number is 6 coordinate bonds. That's what we call the EDT, ethylene diamine tetraacetate. So those are the types of ligands, and we can come back here. So the next on our objectives is other shapes. So these shapes, ideally, they are supposed to be covered under physical chemistry. However, I'll just talk about them briefly. So linear, you know that it's the atom, the central atom, and the ligand actually joined by one bond. Then the tetrahedral, you have 4 bonds. The square planar, same thing, you have 4 bonds. And the octahedral, they are about 6. For example, in the hexa aqua, copper 2 ions, as we are going to see after our nomenclature. So those are the shapes. Then the next part will be the nomenclature, and under nomenclature we shall need to first look at the oxidation, how to determine the oxidation state, because it will be very crucial in our nomenclature.